name is Yoni Groisman, and I'm an application engineer in Ophir Photonics. And today we are going to talk about various BeamGage products we have in our product portfolio. So we'll go over the product line of BeamGage. We'll see different accessories and see a few examples of BeamGage applications and usage. So Ophir's current product line, including various beam profilers designated for different wavelengths. The major product line is our silicon CMOS sensors designated for wavelengths from 190 to 1100 nanometers. The next family is some phosphor-coated sensors designated for sphere region and the popular 1550 nanometers eye-safe wavelengths, and also our in-gas cameras for thermal imaging, which are intended to be used in NIR and sphere region, and our pyroelectric sensors that are designated to measure entire spectrum from deep UV 13 nanometers till up to millimetric waves. But today's topic is mostly our silicon CMOS sensors. If you have any questions during the webinar, you are welcome to write them in the question section, and we'll try to address them during the webinar. So until recently, Ophir's most advanced camera was the SP932U. This camera has 3.45 micron pixel and a wide dynamic range. It enabled measuring various beam parameters, and for NIR beams, we recommended using the blooming correction algorithm, which was developed specifically for NIR beams. The blooming effect is caused by NIR light that is scattered on a periodically placed pixels, and this scattering causing, as you can see in this image, let me enlarge that, the NIR beams are scattered inside the silicon, and this causes broadening of a beam. For example, you can see that this blooming causes this area to be black and the beam to appear larger than its original size. So the implementation of the blooming correction algorithm in our BeamGage software enabled us to remove that blooming, and the beam size would be more accurately measured with this blooming correction. So instead of ignoring this effect, like some of our competitors, the BeamGage software actually corrects this blooming factor. Recently we added a few more cameras to our high resolution beam profilers product line. I'm talking about the SP204S, which was previously only used in our BeamSquare device and now also sold as a BeamGage, and the SP402S with 1-inch large format sensor, which replaces the LT665, our previous camera with a large 1-inch imager. So both new beam profilers combine a high resolution and high accuracy, all in a compact footprint, and they actually complete Ophir's migration from some outdated CCD imagers in favor of more advanced CMOS technology. So both cameras equipped with one of the highly resolved sensors in the market with wide dynamic range and small pixel pitch, enabling very detailed beam characterization. So let's go over a little bit. Let's see the specification and compare them to our existing portfolio. So the SP204, as I said, it employs quite highly resolved backside illuminated sensor. It has a very small pixel pitch of 2.74 microns, enabling us to measure beams as small as 27.4 microns, because we need 10 pixels to cover a beam in this proper resolution, compared to the SP932U, which had 3.45 micron pixel pitch. And also the frame rate is much faster. In full resolution, it's now 37 frames per second compared to 24 frames per second for the SP932U. However, still because the SP932U uses the blooming correction algorithm, we still continue to designate it for tightly focused NIR beams. But all the rest of the users, we do recommend using the SP204S. So to summarize, for majority of users, we recommend the SP204S, unless you have a tightly focused NIR beams somewhere between 37 to 100 microns, and then we recommend you using the SP932U with the blooming correction algorithm. Okay, so now the new SP402S, which also have a very well resolved back illuminated sensor. It have a quite wide imager area of 1.1 inch. Actually, the active area is 12.3 by 12.3 millimeters compared to our previous 12.5 by 10 millimeters LT665 camera. Also, the pixel spacing is just 2.74 microns, enabling measuring beams as small as 27.4 microns and up to 12.3 millimeter of top head beams. The dynamic range is much wider than the previous camera, than the LT665. It is now 67 decibels compared to 45. And the only downside is slower frame rate, which is now 11 frames per second compared to previously 27 frames per second. But they can be easily increased. The rate can be increased by either binning of the pixels or limiting the region of interest. And of course, the footprint is much smaller than the LT665. Actually, all our cameras, all our standard CMOS cameras now have the similar footprint, just the sensor, the imager area is larger. If we compare the actual beam characterization between the two cameras, between the SP402S and the LT665, let me enlarge the image. We can see that the LT665 for beams above around 70 microns show slightly larger beams, and this is due to the blooming of the LT665 camera. You can see now that above 70 microns, the red line represents the LT665, and it shows larger beam size than the SP402S. And that's because of the blooming effect in the LT665. Let's see some images. If you notice here in the LT665, the beam size it appears larger. It has some blooming effect, and actually the beam size is 135 microns. Same beam with the SP402S camera shows 122 microns. And this is because the blooming effect is much smaller in the SP402S. And also in the LT665, you can see a significant pixelization of the image, which is barely noticeable in the SP402S. There is almost no pixelization due to very high resolution of the camera. So all of our cameras now have similar dimensions, the SP204, SP402, similar exterior footprint and drawing as the SP932U. all of them have this mount adapter that can be connected from each side, from either side of the camera to ease the alignment. And also we provide, with each camera, we provide a set of 3 ND filters and the C-mount target cap as aligning accessory. Okay, so now the software itself. Our BeamGage standard software is fully functioning software with extensive set of ISO measurement, statistical calculations, and beam maker for laser beam simulation in the software. The BeamGage Professional adds you some more functions like the automation interface, which allows users to integrate all BeamGage functionalities in their system, either using Python or MATLAB, LabVIEW, C++, or Visual Basic. With the purchase of BeamGage Professional, we provide a huge list of all the functions and also examples in all those languages, so to ease integration in user systems. The BeamGage Professional also allows custom calculations, some off-axis correction, which I will show you later, and also multiple beam analysis, which we call a partitioning, enabling to measure multiple beams simultaneously. So now let's go over a little bit and see our accessories and some BeamGage example. So one of our accessories is the CCTV lens, which is mounted on a camera. As you can see some application here. The CCTV lens is mounted on a camera and it looks on a beam dump, and the laser is shot down on that beam dump. So we look on the laser spot from a side. The user can usually shoot a laser beam on some wall or some diffusive screen, and we measure the beam from an angle. We have 2 options for those lenses, 25 and 50 millimeters for different setups, and they are usually used for wide beams, distant measurement, and not to interfere with the laser. So for that application, because the lens looks from some angle and not directly on the laser, we need some off-axis correction in the beam gauge, and let me demonstrate you how it's done. Here we have a BeamGage software. It's not a real beam. I used the beam maker, a beam simulation in that software. So because we view the beam, we observe the beam from an angle, we see some elliptical beam. So in that case, we need to correct it. So the software will simulate the beam as it's supposed to be. So we know the angle that we look at the beam, and we can input that angle here. Sorry, from here. So the beam would return to be circular and not elliptical due to off-axis observation. So let's continue further. Another solution more fit to some field testing and industrial environment is our wide beam imager, which is doing the similar thing as the CCTV lens, but in more enclosed industrial envelope. It's designated for LEDs, VXLs, and other wide or diverging light sources. So in most cases, the apertures of conventional beam profilers are too small to collect the entire spot of a large or divergent light source. And also divergent beams cannot be accurately measured with a regular detector because of the angle, because angle reduces the quantum efficiency of the imager, and thus it would be more accurate to measure the divergent beam on some diffusive screen like we do here. So we have a diffusive screen. Inside we have some CCTV lens that is focused on that diffusive screen, and of course a calibrated beam profiling camera. And then we impingle a divergent beam like a diode on that diffuser, and we can observe it and calculate the divergence and other parameters. So the aperture is 45 millimeters, and it can measure divergence angles, a full angle of up to 140 degrees. This instrument is frequently used for far field measurement of VXLs, for example, some LIV test, where the user changes the current or the voltage applied on a VXL, and this causes both the power and the divergence of the VXL to change. All this can be documented by the BeamGage software, and the charts, the profiles of could be compared in one single chart using some export to Excel or CSV. And this allows the user to perform VXL LIV test with the BeamGage. So let's see a couple of examples and how the user can calculate divergence. So this is a real beam of a VXL in the far field. The VXL is directed towards the diffusive screen of the wide beam imager that you've seen previously, and the wide beam imager captures the image and calculates the beam size. And what user needs to do is input the distance between their emitter and the diffusive screen. Let's say it's 25 millimeters. And the BeamGage software will calculate the X and Y and average divergence of the VXL beam. So another example, it is actually the same beam, but with more current applied to it. So you can see if we input the distance between the emitter and the wide beam imager diffusive screen, we receive now much smaller divergence compared to the previous beam due to changes in the divergence of the beam. Okay, our best-selling accessory is the LBS, a laser beam splitter with some replaceable ND filters. It incorporates both two orthogonally oriented beam splitter wedges and replaceable filters for additional attenuation of the beam to fit the imager power parameters. And if additional beam attenuation is needed, the user can install some external wedge splitter that can be mounted on the input port, or install some main beam, some mirror to fold the main beam to ease the setup. The LBS 300 can operate up to 1 kilowatt, and it preserves beam polarization because two beam splitting wedges are orthogonally located, and it has a C-mount adapter to fit our beam profiling cameras. Each one is equipped with 6 or 10 ND filters mounted on the filter slides. And we offer the LBS in feed for UV, visible, NIR, and broadband to cover the entire spectrum. One of the members of the LBS family is the LBS 300 HP for high power. It's a unique product because here the wedges are not coated, but they have some special patented surface treatment that enables them to withstand extremely high laser power densities. The LBS 300 high power can operate up to 5 kilowatt or 15 megawatts per square centimeter, and it can attenuate an NIR laser by 1 million. Let's see this setup. For example, we can shoot a very high power laser beam through the LBS 300 HP. 99.99% of the initial beam can be directed towards Ophir's beam dump or some water-cooled power meter to contain the beam. 0.1% can be reflected towards some thermal power sensor, and only 1 ppm, 1 part per million, is reflected towards Ophir beam profiler through some extension tube to reduce scattering. So with this setup, for example, you can simultaneously measure a profile of extremely high power laser beams, a beam profile, and simultaneously measure the laser power. Another option for those LBS accessories is the focal spot analyzer. The focal position can change very rapidly with changing of laser power and due to processing like thermal lensing, where the center of a lens hits much more than the periphery, and then it disturbs the beam. And actually the laser can even change, the focal position can change very rapidly. Like in 1 second, it can shift by 3-4 millimeters due to thermal lensing. So the FSA, the focal spot analyzer, designated to identify the exact position of the focal spot. It actually has the same LBS with a beam profiler, slightly different mechanics, but we have the optical pass accurately calibrated with plus minus 50 microns accuracy. The calibration is between the top surface and the camera imager, as I said, with plus minus 50 microns accuracy, and that enables user to identify the focal spot position very accurately. The replaceable filters are also measured and taken into account during the measurement. This FSA comes either with the SP932U camera or with the new SP402S camera. Another camera we offer is the SP504S camera. This camera actually have a huge imager area, 23 by 23 millimeters. Although the sensor is huge, the pixel spacing is still very highly resolved. The pixel spacing is 4.5 microns, which enables us to measure beams as small as 45 microns. And used for LED measurement, wide beams, or beam tracking when the beam position is not stable. In case the beam is relatively high power, we offer some accessory called LBS 400 for beam attenuation. It's similar to the LBS 300 that I showed previously, but in this case, it have a very large clear aperture of 32 millimeters, and it can fit UV, NIR, or even infrared lasers, and it can withstand laser powers of up to 1.2 kilowatt. Additionally, our accessories contain different re-imaging beam expanders and beam reducers, different re-imaging optics. For example, re-imaging beam expanders allow us to expand the beam to increase the resolution with those beam expanders that we offer in 4x, 6x, 12x, and even 22x, we are able to measure beams as small as 1 or 2 microns. On the contrary, our reimaging beam reducer enable narrowing the beam by 4 times, and so it could fit the imager area. It's used for collimated beams. We offer all those accessories also with UV converter option. In UV converter option, where we, in addition to the reimaging optics, we have some UV converting plate that absorbs UV in a region of 190 to 350 nanometers, fully absorbs UV and emits a green light. And this green light is later imaged by this reimaging optics on the camera sensor. This enables regular CMOS cameras to absorb UV light, which would be otherwise invisible to silicon sensors. All those accessories are also available with some additional external beam splitting wedges to reduce power. Now let's see some of our OEM solutions. For example, this what we call a near field analyzer for VXL measurement. The near field analyzer uses some microscope objective, some folding mirrors. Inside there is some optics for highly accurate imaging of VXLs, and it enables measuring both individual VXL emitters and the entire VXL array, as you see here. All this with having a high image quality and high resolution, and enables also measuring up to 35 degrees divergence. The numerical aperture of these systems enables measuring up to 35 degrees. And the field of view is also quite large for VXLs and is 2.3 by 2.8 millimeters. So we developed this OEM solution for a user that needed to measure VXL arrays and in the production line, directly in the production line, and as part of the production QC. And if you can see here, let me enlarge the image. The BeamGage software enabled them to identify and detect defective VXLs and to sort them out, and thus having some quality control. So together with BeamGage software. Due to the ability to fold the beam, we were able to make some compact design, and also we provide a large selection of replaceable ND filters to fit various VXL powers, either in pulsed or CW mode. I'll show you an example of how it looks in BeamGage. So this is actually the measurement of a VXL using this near field analyzer OEM, and I want to show you how we measure multiple beams simultaneously. So in BeamGage Professional, we have this function called partitioning, where we can choose each aperture for different beams, and we can simultaneously mark several apertures, and this will enable user to measure a huge array of VXL emitters simultaneously, and the user can look one by one each aperture simultaneously or one by one. And also we recommend integrating this in the factory system using our automation interface, so it will enable the user to measure each VXL individually and all the entire VXL array simultaneously. This is how it looks in 3D, by the way. So in general, Ophir attempts to release all the products to be interconnected. So here are, for example, couple of examples of this connection of our products. We use the LBS laser beam splitter with the 4x beam expander and a camera to both reduce the power and expand the beam to increase resolution. Or another example, some LBS 100 beam splitter with replaceable ND filters, but this time it is mounted with the beam reducer to fit a collimated beam to the imager size. In general, most of our products can be interconnected between them using various mechanical adapters that we also provide. So how does one knows which is the best solution, which camera fits them more, and which accessory do they need for optimal setup? We have this function called the beam profile finder, and I'll show you a couple of examples now. You can reach it from our website, the beam profiler finder. And let's see a few examples. For example, we have some focused beam. Let's say the beam size at the focusing lens is 5 millimeters. The beam is a green laser with 100 watts laser power. And we have like 200 millimeters laser focal length, and it creates 100 microns beam focal spot. Let's see what the beam profile finder will offer us. So it offers different products, including nanoscans, which we did not cover in this session. It also offers us the SP204S camera with LBS laser beam splitter fit for visible lasers, or it offers the same set but also with some beam expander to increase the resolution of the beam measurement. Let's see some other example. Let's see also focused beams, but this time it would be a pulsed beam. Let's say 7 millimeter beam diameter on a focusing lens, NIR region, and we operate at 50, let's say 50 millijoules. 250 focal lengths of the lens, and we create a 50 microns laser beam, 50 microns focal spot, and we operate at 10 hertz with with pulse width of 10 nanometers, for example, some typical laser. So now the beam profile finder will offer us the SP932U beam profiler, which is optimal for tightly focused NIR beams with the laser beam splitter, the LBS 300 fit for NIR region. Or alternatively, it will offer us the SP204S camera, but this time with beam expander and also LBS for beam laser power attenuation. Let's see another example. This time, let's take a collimated beam, flat top, a very large flat top beam of 20 millimeters, like some diode, for example. Let it be red, and with some low power of 1 microwatt. So in this case, the beam profile finder will offer us the very large format SP504S camera, capable of catching the entire 20 millimeters of the diode. Or alternatively, it offers us the SP204S camera, but this time with beam reducer to fit the diverging beam to the imager size. And let's see last example. Let's take this time a divergent beam, diverging beam of 30 millimeters in diameter. Let's say 1 watt, and now it would be like UV laser. Because this beam is very divergent, it will offer us a beam profiling camera, but this time with wide beam imager with the alumina diffuser, or alternatively the CCTV lens mounted on a camera as we've seen previously. So please, you can use the beam profile finder to find the optimal solution for your specific setup and laser. So that's the end of the presentation. Now, if you have any questions, please write them down in the chat. So I answer a few questions. Is the beam profile and size checked as sharp focus? I'm sorry, I'm not sure I understand the question. We can measure a sharp focused beams with our cameras, depends on the laser type and the wavelengths. Maybe if you can elaborate your question a little bit, we can have more detailed answer. Question: how can I measure or determine a focal spot diameter and diameter at the focusing lens? So usually users know the diameter at the focusing lens, or they can do some calculation. And the focal spot diameter can be, we have in Ophir website, we have some calculations of laser focusability. But in general, if you need to measure the real focal spot size, you can use our beam profilers with some laser beam splitters LBS we provide and measure the focal spot size that is created. And on a lens, it is usually provided by the laser manufacturer. Could you recommend any beam profiler that can measure optical power and beam profile at the same time? The interesting wavelength is around 450. The optical power is 5 watts. Okay, so the beam profiler doesn't actually measure laser power. It measures photons, it measures illumination. So the power measurement is relative and not absolute. So we, as I've shown in one of our slides, we using our LBS beam splitter, you can make a setup to measure the beam profile and the power simultaneously. Or you can use any other beam splitter and just split the beam half towards Ophir's beam profiler and half towards Ophir power sensor. Would it be more effective to apply blooming correction instead of ultracan when optimizing beam profile accuracy, or does combining both yield a more precise and reliable measurement? Yes, definitely. You need to combine both the blooming correction and the ultracal. Ultracal reduces the noise and the ambient light, and the blooming correction removes the blooming in NIR region due to internal scattering. I tried using the beam profile finder to find measurements for measuring M square, which requires me to image the beam also near the waist. I could not find the match. Could you please tell if some instrument match for a full M square measurement? I have a tightly focused and IR beams. infrared beams at 1300 nanometers. Okay, so in this webinar we did not cover any m-square measurements, but if you would like to send us some email, we'll be gladly send you some information for products fit for m-square measurements of IR beams. In general, we have the instrument. I'll show you. We have this beam square instrument with some in-gas camera that is designated to measure collimated an m square of collimated beams in SWIR region, including 1300 nanometers. But we can provide you more details with some email. So thank you very much. If you don't have any further question, thank you very much for participating, and see you in our next webinars. Thank you. My name is Yoni Groisman, and I'm an application engineer in Ophir Photonics. And today we are going to talk about various BeamGage products we have in our product portfolio. So we'll go over the product line of BeamGage. We'll see different accessories and see a few examples of BeamGage applications and usage. So Ophir's current product line, including various beam profilers designated for different wavelengths. The major product line is our silicon CMOS sensors designated for wavelengths from 190 to 1100 nanometers. The next family is some phosphor coated sensors designated for SWIR region and the popular 1550 nanometers eye-safe wavelengths, and also our in-gas cameras for thermal imaging, which are intended to be used in NIR and SWIR region, and our pyroelectric sensors that are designated to measure entire spectrum from deep UV 13 nanometers till up to millimetric waves. But today's topic is mostly our silicon CMOS sensors. If you have any questions during the webinar, you are welcome to write them in the question section, and we'll try to address them during the webinar. So until recently, Ophir's most advanced camera was the SP932U. This camera has 3.45 micron pixel and a wide dynamic range. It enabled measuring various beam parameters, and for NIR beams, we recommended using the blooming correction algorithm, which was developed specifically for NIR beams. The blooming effect is caused by NIR light that is scattered on a periodically placed pixels, and this scattering causing, as you can see in this image, let me enlarge that, the NIR beams are scattered inside the silicon, and this causes broadening of a beam. For example, you can see that this blooming causes this area to be black and the beam to appear larger than its original size. So the implementation of the blooming correction algorithm in our BeamGage software enabled us to remove that blooming, and the beam size would be more accurately measured with this blooming correction. So instead of ignoring this effect, like some of our competitors, the BeamGage software actually corrects this blooming factor. Recently we added a few more cameras to our high-resolution beam profilers product line. I'm talking about the SP204S, which was previously only used in our BeamSquare device and now also sold as a beam gauge, and the SP402S with 1-inch large format sensor, which replaces the LT665, our previous camera with a large 1-inch imager. So both new beam profilers combine a high resolution